Hello everyone, and welcome to the last lecture of Motion Control Systems class this year. As I have been promising to you that we will be making some examples and we will learn how to implement those control algorithms in the simulation environment, I dedicated the last class of the year for some example studies actually. Uh, but in order to provide you with the widest opportunities, I will try to create simulations both on Simulink and using MATLAB M-file environment. The reason for this is very simple. I'm sure that some of you have the licensed MATLAB of the school, and some of you can reach the licensed version of the MATLAB from the school network. But for those of you who cannot achieve a licensed version, you can refer to Octave, for example, which has the same syntax background with that of MATLAB, and you can write your codes, algorithms over there. That's why you would need to know how to write an algorithm in an M file. Now, I opened MATLAB desktop for you and a Simulink empty simulation file for you. Now, I'm gonna try to simulate a system. First, I'll create the system itself, and then I'll add some controllers and simulate and see the responses here. Then I'll move from here to the MATLAB Empire. As we have always been doing this, before starting with the simulation environment, just go to Simulink and click on the model configuration parameters. Here you're gonna see the solver selection type as variable step, and please change this to fixed step. That's very simple. The difference is that variable step tries to run the simulation with varying time steps. It's not constant. And the reason is very simple. The MATLAB environment tries to collect as small data as possible in order to preserve memory, in order to have computationally efficient environment. But if you're talking about a realistic scenario, we have to refer back to the real-time application, and all of the real-time applications are based on fixed time steps running with a clock. So once you select fixed time step, then from the solver details, you can set the time step here. I'm gonna call this dt, and rather than defining some arbitrary number here, I'm gonna define all of those parameters in a parameters file. So let's click on apply and OK. So let me go to MATLAB and create a new script. By the way, don't forget that your simulation file and the file that should be run before the simulation, that's the parameters file, should all sit in the same directory. So I created on my desktop, I created an example sim file, and a folder, I'm sorry. I'm gonna save all of those files to the same folder. So before we move on, let's write these codes. Close all, clear all, CLC. These are for closing all of the applications that are currently open, closing all of the windows, I'm sorry, clearing all of the information in the memory of MATLAB, and clearing the screen. So our first variable to define here was the sampling time. Let us select 0.001, that is around 1 kilohertz of loop. Not around, that's exactly 1 kilohertz of loop. And since we already set this fixed step size as dt, we'll have the same sampling here. Of course, before that, we have to save this as let's say parameters. And once we save it, you can make sure of it this way. So look at that. There's nothing in the workspace. And when you go back and run this section, you'll have the dt, which is defined to be equal to 1 times 10 to minus 3. That's 0.001. Okay, let's go back to our simulation, and let us first save this as System simulation, system sim. Before you start with the details of the simulation, the very first thing you have to take into consideration is to create a plant. And for the plant, you have to go to the library browser and select from continuous the integrator option. Because don't forget that the plant was simply a double integrator system with division by the mass or inertia of your plant, of your system. So this is one of the integrators. Let me try to zoom for you. And I can add here secondary integrator. So what I did was just clicking on control and holding the block here. Okay, I'm clicking on control and holding the block and dragging it somewhere else. So it asks for the option. You can select paste. So it created a second integrator for me. And you can click, you can actually pull the cable from one side to the other, or simply you can click on the first block, click on control and click on the second block. So the first block is attached to the second block this way. That's also another option. Please make sure that you have solid connection between those blocks, because if the connection is not successful, you'll have this red line, and if once the connection is successful, you'll have the line to be converted to black color. I have observed many times that the students are having problem with this because there is somewhere missing some small connection, and in a big simulation it's not easy to observe. So make sure that your connections are solid. This is simply a double integrator system. And before the double integrator, we have to put here division by mass. That is, from the math operations, we have to look at the gain block. Here is the gain. We can give it this way, and simply we can write in that should be equal to nominal mass, but it's not Mn, it should be equal to 1 over Mn, right? Okay, now you cannot see it. Let me try to expand it a little bit for you. Okay, 1 over Mn. So simply you have 1 over Mn integration and integration. Now, here all of the torques should come, because if you remember, summation of the torques were being divided by the nominal mass of the system and were being then double integrated to yield to the position of the system. So here you have simply Q plant. Here this line is for Q dot and this line is for Q double dot. Maybe we can put a little bit more space between them. Okay, here we have to put the summation block. They're all in math operations, by the way. Don't forget to have a look at this summation block. And what I usually do is to change this to that scheme. It is plus and minus here. No, it is minus and plus. Let me minus and plus. Because our input torque will come from this side and the disturbance torque will come from this side. And disturbance acts on the system with a negative sign, right? So far so good, I guess. Now let us think of a disturbance term. Well, we may think of a system that has the friction, viscous friction, that has potentially the gravity effect, right? So let us take this. Let me take here some signal and multiply it with the friction coefficient of my system. Let me call this B. So B times Q dot is what we have here. Now you can also pull another block here, that is going to go into a function. Well, if you consider the gravity's effect, you may call this as a scale of the cosine of system's angle, for example. Think of this to be a rotary system, right? And you can call this because if you think of some rotating system, you have the angle q here, then cosine q, right? mg times cosine q is the force. Or in other words, let me move to the. I'm sorry, just a second. Okay, I think we can move on here. So what I'm talking about is nothing but this. Suppose you have a system, single degree of freedom, right? And your system's position output is given here as q, and you have the mg term here, right? So if you zoom on this side, what you're going to encounter would be something like this. You have, sorry, you have this angle being equal to q, right? And you can call this term and this term as, for example, this term will be mg times cosine q, right? And then there will be certain scaling like L over 2. So we can call the gravity effect, so G of Q can easily be called for this system as mg cosine Q times L over 2, right? So it's a function of the cosine of position response. Let me keep these in my file and go back to my MATLAB file. Okay, just a second. I think we're back. All right, I was trying to solve the problem with the recording environment. All right, now I have to simply add a function here that takes the cosine of the response and multiplies it with a scale. So let us take from here a user-defined function. I think f of u will sufficiently help us to result in the function that we need here. Okay, we can write here. So in this environment, you have u as your input, and if you have multiple inputs, u of 1, u of 2, or the first component of u, second component of u, will be the items connected in series. But we have just one variable connected there. We can call it u, and we can have a look at cosine of this u, and we can write here a times cosine of u. If you expand this, you will basically see the content. Okay, so let us assume that these two effects are simultaneously acting on my system as the disturbances. And of course, before moving there, I have to be able to connect those two. I can move from a round representation to a rectangular one and simply put two plus signs, which means in a rectangular environment I'm going to add two signals. The first one is this, and the second one is this. Let me try to adjust the distances for all of you. I think this is a better looking system. Then we can create the feedback in our system. So simply we can call from this point to this point, from this point to this point, we can call the system as plant. So this is our plant. Why did I pick it this way? It's very simple. because your plant is consisted of a double integrator structure with a scaling with the nominal mass of your system, your motor, let's say, and with internal feedbacks as the viscous friction and the gravity terms. Of course, these are not only the forces that are acting on the system. Without loss of generality, you can simply add here another term. You can add here another term that is from external forces or torques. Okay, let us assume that there is some constant external source, which I will be calling as F external. Now, once we define all of these details in our system, we have to be very careful about one thing. The system we developed here should also include, from the math operations, the scale, the gain that's here, and this gain should include Kn. So we're gonna simply play with the system by manipulating its input current, and the input current will be multiplied by Kn in the driver side, and we'll go to our plant with certain input torque from the driver, and our plant's response will be observed thereafter. I think so far so good. Now we have to go back to our definitions file and try to define all of these parameters. Let us start with Mn. We had a term nominal mass. I'll try to be consistent with the variables or values we had in the system we're running in the lab. I think 0.255 would be a good approximation for that. The nominal torque constant would be then 1.8. Let me go back and define here the B and A terms. B, the viscous friction term, the viscous friction coefficient scale can be taken as, for example, 12. And A cosine U, I think A can be 0.3 here. And F external can be defined as 1.2 newtons, right? Let me see. Actually, yeah, that's okay. 1.2 newtons is okay. Once you save all of them and once you run them, they're all going to be defined in the workspace of MATLAB, and our system simulation file can now take these variables from the workspace and run the simulation with those variables. But of course, if you run the simulation as is, you'll not get anything. Let us try to give some constant input. So let's give some constant source here, like 1 amperes, because you're giving the current here, right? Input current 1 ampere, and let us try to observe the responses of the system. And in the responses, I'm gonna use the sinks and simple scope function of MATLAB, and I'll be observing all three of the position, velocity, and the acceleration. So this is position, this is velocity, this is acceleration. Oh, I think because of my camera you cannot see this right bottom corner. Okay, here is it. Position, velocity, acceleration. Now, with all these parameters, I think we can run the simulation. When you click on this running function. You'll be running it for 10 seconds, and let us try to observe the response of the system. In the position response, we have a directly accelerating system because the current variables are not so effective. And if I change this to 0.5 amperes and run it, then there will not be any difference, but okay, there is difference. Because of the gravity effect, it tries to fall back. I think 1 ampere was enough, and in the velocity term we have this. So as our q changes its value, we first reach the constant speed, and the speed then increases, and possibly it's gonna decrease at some point. Let me try to change the simulation time to 50 seconds and try to observe what's gonna happen. Okay, our system blows up very nicely. So if we want to inspect the reason for this, the system first overcomes the friction and the gravity effect, and then moves further for the acceleration. So if you look at the acceleration, you're going to see a strange pattern that is reducing. I mean, it makes a peak at the first moment and then goes to 0, but it's not exactly 0 actually. If you zoom there, you're gonna see that it's diverting from 0 to some value, which is actually the main reason for the acceleration of the system. If we try to play with the parameters, for example, instead of a cosine q, and instead of this with the value a is equal to 0.3, let me try to put here a is equal to 2 and try to observe what's gonna happen in my system. So click on this and have a look at the velocity. Okay, now we have a different structure. Well, all of these parameters are somewhat affecting the response of our system. If we increase the friction coefficient, viscous friction coefficient, or decrease it, if we change viscous friction coefficient to 3, that is 3 times the velocity of our system, we can also get a different response from the same system. Okay, now we have different response, right? And it turns out that the velocity reduces to 0 value. This is simply due to the fact that the gravity effect moves the system down, and your current is not enough to push it back. If we increase this input current to 3 amperes, probably we're gonna see a better response. Okay, now we can see that the current starts to run our system. It moves the system up, and as the system falls down, it increases its speed and then decreases because of the rising edge, and increases and decreases. So it's in a sense oscillating this way. And of course, the corresponding position response will behave similarly. Okay, I think, yes, this is the position response, like this, creating circles for us. Now, no matter what we have from the position, velocity, or the acceleration, if you look at the acceleration, you're gonna see also strange patterns. Okay, that is our plant. Let me try to cut the connections here, take these scopes aside, and try to focus further on this side. So this is our plant. Now, I'm going to try to understand or implement actually a disturbance observer on this system. Because if you remember, input current being equal to 3 and Kn was equal to, let's look at this, 1.8. So 3 times 1.8 and Mn is 0.255. If you calculate 3 times 1.8, this is the given input current as a constant value times the nominal torque constant. That's 5.4 Newton meters. And if you divide 5.4 by the nominal mass of the system, you should be able to see some acceleration equal to 21.17 degrees per second square. Yeah, there's no mistake there. So, however, we see something else. If we had a look at the acceleration again, we do not see this value, right? That's simply due to the disturbances acting on the system. And if we try to implement a disturbance observer structure here, we're gonna see that its compensation will be much better. So, how do we do this? Disturbance observer is actually an algorithm, as we have always been defining. And this section, the rest of the section here, the disturbance observer, will be what you're gonna be typing your coding in your real-time controller in a real application, whereas this side of the system will be sitting as is as the plant of the system. So you don't have any chance to play with the internal parameters, but you have chance to create an observer and kill the disturbances in the system. So I'm taking the input current from the reference and multiplying it with Kn, and I'm assuming that I can measure the velocity of the system somehow. And if you remember, we were trying to multiply the velocity with Mn and G term. G was the cutoff frequency of our disturbance observer. If you add these two signals here, and apply a filter, a low pass filter, so let us try to squeeze them, M and G, Q dot, and here we have the transfer function, this one, and the content of the transfer function should be G over S plus G, if you remember. Okay, here's what we have. And finally, we were trying to subtract the results, so we have to change the signs as plus minus, I think. Yeah, we were trying to subtract from the result another Mn-G multiplication. The derivation for all of these are in the lecture notes, and we have made this several times actually. That's why I'm pretty comfortable on this, that you have recovered the details. Okay, here if you take the signal, this is the disturbance torque, estimation of the disturbance torque, and if you multiply this by 1 over Kn, then you're gonna have the current generated in the system, that is the equivalent of the amount of current consumed by the disturbance of the system. So if you feed this forward, let's take this to be something like that. Actually, I can have it this way. and that one. Okay, if you feed that current back to your system, then you have to be able to compensate the disturbances. Here we have to keep in mind that G was not defined. Let me go back and define G to be for this simulation 1000, and then we can play with this value later on. Okay, if we now run the simulation and try to have a look at the responses of the system. These are the position response, the velocity response, and possibly the acceleration response. Well, maybe acceleration can be taken here actually. Okay, we're going to run the system with this, and okay, G doesn't exist. This is natural because we have written it here but we didn't run this. You can understand this from the parameters here. There is no G, right? Once you run the simulation, run the parameters file, then you have the G defined here, and then you can go back to your simulation and try to run this. Okay, it's completed. Now let us have a look at the acceleration. Okay, the system's acceleration is moving up and down because the disturbance is continuously changing, but have a look at its mean value. Mean value is somewhere here, so it's almost 21, right? If you go back and look at our calculation, we were expecting 21.17 or 21.18 to be our acceleration response, and disturbance observer provides this at the beginning, except the fact that after a while it starts to oscillate like crazy, which means that we might need to adjust the parameters further. So let us go back and try to select disturbance observer cutoff frequency as 2500 and observe if we're gonna have any change in the system. Okay, now the accelerations at the beginning oscillate too much, but later on they are in a more consistent pattern. If you actually look at this, the mean value is again 21.1. So your observer tries to catch up with the required acceleration, and be careful on one fact, that these oscillations are not due to a problem in the controller. They are basically because of the rotating system and varying disturbance acting on the system. So if you look at the disturbance term, so for example, if you look at the estimated disturbance in your system, this will be disturbance, right? What you're gonna see is something like that. Your disturbances are increasing, but there are continuous oscillations on your disturbance. Can you see these? And because of these oscillations, your system gives oscillating accelerations in the response. Now, if you remember, the disturbance observer was derived based on the assumption that the disturbance acting on the system has low frequency dynamics, because the remaining disturbance was equal to the derivative of the disturbance low pass filtered and scaled, right? So because of this, we can assume that if you have high frequency changing disturbance in the system, you'll have less accuracy in disturbance compensation. But of course there are other parameters acting on the system. For example, if we go back and change the simulation time from 0.001 to 0.0001, run this and try to run the simulation, but 50 seconds will then be too long. Let's run this for 20 seconds. So I basically increased the sampling time, and I'm trying to observe what's gonna happen. Okay, acceleration. Can you see? The accelerations are now much better, the response is much better. It's again not fixed, it's still oscillating later on, but if you look at this value, it's almost the value that we were demanding from our system, right? Okay, somewhere here, 2107, very close to what we had. Now if we play further, go back and change this to 4000, for example, we're gonna see that the acceleration response will get, hopefully will get better. So let's see. Doesn't have too much change, but it's a little bit better. Okay, now you can play with all these parameters and see the effect. For example, if the gravity effect is not that big, but it's smaller, then the response would obviously have different behavior like this, right? If the friction coefficient was not that high, or if the friction coefficient is bigger, so let's say 1.5, half of the value we have, then the system's response will change also accordingly. So that's what we have for the time being. Now, if you remember, in all of our controller derivations, we were telling that the disturbance observer here, that thing, is a good tool to compensate the disturbances in our system, but it's not only enough to control our system. So for the simplification and for further analysis, I'm gonna make some changes in the system. So I'll cut this and this from here and this input. I'm gonna try to connect these two on the same line and that as the output and this as the input of my system, and simply I'm gonna call this the disturbance observer. I'm right clicking and selecting create subsystem from selection. Okay, this is DOB, disturbance observer. And if you look at the structure inside, you have input 1. The input 1 was actually Q dot, right? Input 2 was I ref, and this was this disturbance current. If you save and if you go back to the main simulation file, you have that structure. So I think we can simply play with this. Here we have the Q dot response. Here we have the I reference. Okay, and the disturbance current should go back to this part. Or you can simply rotate this to have a better structure, and you can play with the positions instead of QD and IREF in those order, in this order. You can change this as to have the second value and the first is here. All right, here is this structure looks much better. You have the disturbance observer that takes the reference current and velocity of the plant and gives you the disturbance current. Now I'm gonna break it here to create another subsystem from this selection. which will be called the plant. But I made a mistake before creating the plant. Let me take out its position and velocity signals, and let me try to create subsystem from this selection. Okay, we now have the plant. What's this input one? Let's see. Input one is simply input current. I input. That's equal to the reference current plus, no, that's actually reference current. That's not input current. That's IREF. Okay. So you have the plant here. All right. And this plant obviously takes the velocity response, and it has the disturbance observer structure. Okay, it's in a nice and compact manner. Now we have the plant and the disturbance observer all together in different blocks, because the plant itself contains the viscous friction, gravity effect, external torques, everything acting on the plant sits here, and your plant takes only the reference current, and you can measure the position from your position response of your plant, and possibly by using some estimation methods you can gather the velocity response, or sometimes some advanced encoders are also giving the velocity response of your plant. And based on the velocity response and the reference current, we can construct the disturbance observer. Don't forget that this is sitting in a place outside the computer. That's the real system, and that part, DOB part, and of course the reference current part, okay, all of these blue shaded parts are in your computer except the plant itself. All right, now instead of giving the input current this way, I think most of you already remember what we were doing. We were generating some error. We were trying to pull that error to zero value, and let us try to change the system a little bit more. So if we put here from the math operations a gain function, okay, that's our gain, and if we select the gain to be m nominal over k nominal, okay, m nominal over k nominal, just a second. All right, that's better looking. I can insert here the desired acceleration and try to observe the acceleration response of my system, right? Actually, we can take a third response that will be equal to the acceleration, QDD. All right, now I have the acceleration response and the desired acceleration. If you try to plot them on the same graph, what you're gonna see is something like that. Let's put here some sources as, for example, the sine function. Where is the sine? Where is the sine? Okay, sine wave. Some arbitrary sine function, 1 time sine 1t with 0 phase, and sampling time should be, of course, dt. It should take the same sampling period. So let us try to observe this and the response together. Well, for observation, you can use the sinks and scope. The new generation of MATLAB has a 2-input version of the scope, but for those of you who do not have the latest versions of MATLAB, I'm recommending you to check out the signal routing, and here you'll have the multiplexer. A multiplexer is nothing but a digital operator that combines signals on one line. Okay, so we have the reference acceleration and response acceleration of the system. Let us try to see the response, see the output. Okay, if you observe here, if you zoom basically here, you can see that they're one-to-one matching, and our reference and response accelerations are exactly on top of one another. So this is actually showing us the power of the disturbance observer, because if you remove the disturbance observer and try to plot those two variables, you're gonna see totally different responses. Can you see this? The yellow one is the reference acceleration and the response acceleration is the blue one. Okay, so if you look at the system with disturbance observer, then the acceleration reference given to our system, this is QDD desired, right? The desired acceleration will match with that of the response. But if you just consider that there will be again small tracking errors like these, right? Very small tracking errors like these, then it's obvious that this tracking error will be double integrated to yield to a system that's diverting from its reference. That's why you need a controller here. And in the controller, our objective is to create the desired acceleration, which will be then traced by the system, by the plant with the disturbance observer. Now, let us move further. Well, simplest controller that we were driving in the class was, I remember, the velocity controller. For this, you would need a velocity reference. So let me pull back those signals. Let me assume that this is my velocity reference. And if you remember, our desired acceleration was then equal to the reference velocity, right, minus the response velocity, somewhere here. Okay, we need some summation block like this. Reference minus response. Perfect. Plus, we had the feed forward term, if you remember. So we have this, we have that feedback from the system, and we were trying to put here the feed forward term. What's this feed forward term? Let us remember. Let us go back to our slide set and try to drive it once more. If you remember, we were simply having this error was equal to QRef minus Q response, right? And error dot plus K times error was equal to Q double dot ref minus Q double dot response plus K times Q ref minus Q response was equal to 0, because we were trying to set this to be equal to 0. It was actually E dot plus K E is equal to 0, and its implementation was like this. So from this we were extracting the response acceleration and sending it to the other side, right? That was equal to Q double dot response, which was also called Q double dot desired at this time for a plant with disturbance observer, because we know that the response acceleration will be equal to desired acceleration, and we have just shown you the example on the simulation. So q double dot response that's equal to q double dot desired should be equal to, so if you pull this to the right hand side, it's going to be equal to q double dot reference plus k times q reference minus q response. Okay, so we put there k times q res, but this term acts like feed forward term. Now we're gonna try to add this back to our system. Let me keep those values and let me go to my simulation. So my original function was 1 time sine 1t, right? Exactly. So if you take its derivative, you should have 1 time cosine 1t, which means 1 time sine 1t plus pi over 2 phase, right? So this term is directly added, but it's not added here. We made a mistake. We have to, sorry. Okay, we have to first change this to plus minus structure. I think it's now okay, right? And we should put the controller gain here, k or kv I can call this, right? That's the velocity control coefficient, and on top of this I'm gonna have directly feed forward term from the acceleration. So this is basically, this side is our controller, right? That's the reference minus response qref, I'm sorry, this is qd reference. Here you have q double dot reference, and here it's basically qd reference minus qd multiplied by a scale plus the double dot reference is our desired acceleration. Okay, now this kv is not defined there. If you remember that kv here, the k gain was from this equation, and it was simply the exponential convergence rate of our error to zero value. So if we take it to be a something small, let's put here kv is equal to 3, we're gonna have small and as relatively slow convergence to zero value. Let's first run this, and then now we can run that simulation. It's okay, but we have to look at the tracking actually. Tracking is simply here. I have the reference, and I can take from here the response of the system. Let's see. Okay, reference versus response. If you look at this point, you're gonna see that the error starts from non-zero value and converges, right? Let's try to change the disturbances. No, not the disturbance. Let me try to change the convergence rate from 3 to 0.5. Okay. Tracking is not as highly qualified as the previous one, but still there is very good tracking here. I think we may try to increase the disturbances to see the effects in a better way. So let's take the viscous friction coefficient to be equal to 5, the gravity effect to be equal to 3. Okay, and let's run the same simulation. It's still good, but you can now see that the tracking is not that nice. And if we play with this further, let's put here 0.1 and run this back. Alright, now you can see that the tracking is not that good. Well, another way to look at the response is to see the error. You have the error already defined here, right? You can take this and try to have a look at the change of error in time. Not necessarily for 20 seconds, but let's have a look at it for 5 seconds. And of course, be careful on one thing. Here, we're assuming that the system does not have any initial value, any initial velocity. If you'd like to insert some initial velocity, go to your plant and, okay, double click on this. So this is the integrator that creates the velocity output from the given acceleration, right? If your system has some initial value, you have to insert this here, initial condition. Let us try to go back to scope, and it's around 1. Let me try to put here 0.3 radians per second as the initial velocity of my system. Now if I run the simulation once more, okay, I think it's now observable that the initial velocity is at 0.3 and it goes in an exponential way to 0 value, right? And stays over there throughout the simulation, throughout 5 seconds. Okay, of course, if you zoom here, if we look at the first 0.1 seconds, so it's 0.1, we're gonna be able to see the convergence here, right? I'm sorry, okay. Here you can see the convergence of error to 0 value. But if you go back and increase kV to 10, remember this plot once more, okay? Let's see what happens with 10. Can you see? It's much faster now. So in a much smaller time, it converges to 0 value. Right? Okay. I think we have played enough with the MATLAB Simulink side. In the next video, I'm gonna try to show you how to create a similar simulation in the M-file environment, which will be very useful for you if you want to create your simulations in the Octave environment. Thanks for watching.